company is 120 years old. And what that means? That means two things. One is CEOs after CEOs used to say that clients, they are the reason for our existence. So what that means is we have been serving a number of clients, enterprise clients, for the last 3-4 generations. And what it means, the second is we have huge amount of experience serving the clients in the form of best practices, reference architectures, and other experiences and insights and learnings, most of it coming as the first of its kind, being such an old company. So this is not going to be a true reflection of 120 years of experience of client debugging. Nobody may have a single, as a single source of experience for that, but we have tried our best to meld our own experience of debugging Java and other language framework based workload debugging and integrated with IBM's own best practices, etc. So that's what we are going to cover in the next 1 hour or so. Let's make it interactive, please. At any point in time, if you have questions, please ask. The whole idea is not to complete the slides in 1 hour, but mostly around take away some values out of the whole thing, because it's a huge experience. Not expecting to cover all the field stories in one shot, but let's look at what all we have to cover today. Start with, we have some postulates or high-level theories around debugging, which can be applied across the board for any languages, not just necessary for Java. And then we look at some of the tools, exemplary tools which are used typically for debugging. Then we look at some of the methodologies with which we can use with the tools. And then we introduce local recreate as a very powerful form of debugging. And then we combine everything to showcase some of the real world field stories which actually made use of most of these best practices, tools, and the postulates. That's the whole storyline looking like. Not expecting realistically based on the timing to cover as many field stories, but we'll try to at least cover 1 or 2. So the whole idea is bring in the theory, bring in the best practice, and showcase some of the things that we really did in the field, and then combine it to make the complete storyline. So that's the whole idea. Just wanted to poll in how many of you are Java developers or know Java. So it's almost like 75%. Okay, that's good. So 75%, 3/4 of you are going to have complete alignment with what we are talking about here. For the rest of the folks, it will be a complete learning. So it's a win-win. Okay, let's get into that. So the first one is debugging art and science. It's going to be largely theory. Don't worry about that if it is boring. Next one, we'll talk about methodologies. It will make it a little more clear. But when it comes to the tools and the actual field stories, we'll combine it back, and then the whole picture will become very, very clear.
The first postulate is a proper mindset. This is a general principle for any problem that we approach. The right mindset is very important, much more than you think. The first thing you should have is the right attitude. Especially when it comes to debugging, you cannot go with your personal intuitions or your personal bias. This is not the place to apply that. You have concrete evidence in front of you. You should only use your logical reasoning to proceed. Never form a judgment without checking, without delving into it. Never form a judgment based on what you see, because the story might be entirely different. And the second thing that you should have is the right conviction. You should believe that with the right diagnostic data, it is possible to successfully debug any issue. So that conviction should always be there. And the right approach, like I said, you should always rely on logical reasoning. And your logical reasoning, the way you think, the mindset is actually very important in determining what kind of methodology you need to use, what kind of tool you need to use. Because in debugging, in most of the cases, it is the way that you approach the issue that actually matters.
Yep. Another point is abstraction. Abstraction, I mean, comparative to Java abstraction, what do we do in abstraction? We elevate the instances and make generic classes, which basically provides a guidance about how the derived class should look like. That's abstraction. So in this debugging scenario, Abstraction essentially means look at the anomaly site, be it a crash or a hang or whatever sort of problems. Look at the immediate source of the problem. You can't operate at that level. You cannot devise any debugging strategy. Let's say an IO exception. What problem, what solution you're going to provide, IO exception. Will you put it in a try-catch block, or will you look at the previous line, what happened, things like that. So the most comprehensive way of doing it is look at what caused IO exception. Maybe there is a socket exception that is happening, and that eventually led to IO exception. And then socket exception immediately means there are two endpoints that is communicating, and either the connection or the data transfer resulted in a socket exception. So immediately you start looking at the higher order, right? And look at the name of the services which are imparting in the exception. You get something like a microservice, an inventory microservice, for example, trying to connect with an inventory database, and that's where the socket exception comes. You can keep elevating, you can keep abstracting the problem statement, go beyond that, but at some point you stop. This is the right level of abstraction. Say two microservices trying to connect each other, they end up in socket exception. That's the point you stop, and that's the point you basically start devising a problem statement, devise a diagnostic strategy, devise what sort of tools to employ, and things like that. For example, when there is a socket exception, you will start looking at both endpoints, the error codes. Maybe you will employ a network diagnostics, such as a Wireshark, things. So at that point in time, you have a clear picture about what needs to be done. It's not a point where you know the problem. It's a point where you know how to state the problem.
Okay, so next is isolation. So abstraction, we know it's a top-down approach. Isolation, on the other hand, is a bottom-up approach. Top-down approach and vice versa. So in abstraction, you are looking down at the issue from a high level. In isolation, you need to go down, further down, get to the root, and find out what it is that is causing the issue. So many times in enterprise level applications, it will span thousands of lines of code. It is very difficult for you to run the entire thing in order to isolate the issue and get a solution. It's simply impossible. For example, I work in Eclipse. So particularly in Eclipse PDE, there are just so many files. So sometimes without isolating the particular class file from where you suspect the issue might have originated, it is difficult to read through all the class files to get to the root of the issue. So isolation is basically separating the code where you suspect the issue lays from the rest of the system. And this is very important. And another important thing to note here is how do you isolate? You do that with code flow and data flow. That is, you have the data, you have the issue, you know what has happened, and then you have the code flow. You have the call stack, you can examine, you can get to the root. So how isolation helps is, while abstraction is helping you to form a holistic idea, to define the problem on an enterprise level and so on, isolation will actually help you in solving. And it also saves your time and your effort, because when it comes to business level issues, you don't have a lot of time. So that is isolation.
Yeah. Next one is extrapolation. This is one of the core part of the debugging. As she said, don't believe in myths or personal beliefs. It's more about logical reasoning. So when you have an anomaly, how do you apply the logical reasoning and figure out what is going on? One of the main ingredients is extrapolation. Using extrapolation, you have the data at the anomaly site, but there are a lot of things that happened in the past which led to the anomaly. So for example, if you are talking about a crash, there are a lot of instructions that got executed, and the badness actually got percolated, and eventually it manifested in a crash. So are you just looking at the crash site? No, you need to backtrack. How do you backtrack? The execution has stopped, it crashed. You just have the final data. So you need extrapolation. So the picture is very convincing here. When you do when you have a ligament tear, you don't tear open your leg to figure out or confirm it, because somebody else who had a ligament tear in the past, in the very first time in the history, the doctor would have torn it open and confirmed that this happened. But since then, the mapping between the X-ray or any scanner and the actual happening that is inside would have taught us, if this is how the shape is, this is what it is going to be. So next time onwards, you just need the scan image, you know what is happening inside. So similarly, if you had that data in the crash site, you go backward and see what data would have produced this data.
So next is fabrication. Now, this is more related to recreating the problem locally in your own development environment. Many times, simple debugging or backtracking is not going to provide you with a proper solution. You need to actually know what must have happened in production. What is it that went wrong? So in such cases, you go for fabrication. Fabrication, as the name suggests, is forging the app or tweaking the code which you have in your local environment to recreate what must have happened in production. Now, the idea is to tweak the code to recreate the issue based on your assumption. It is not about changing the code logically. Do not change the code logic because you don't want to create a completely new issue. You want to recreate the original issue in the production. So, fabrication in most cases will help you walk through what must have actually happened in production and what went wrong.
Yeah. Another one is speculation. Speculation is around making new theories. When the original theory fails, the abstraction fails, or is not going to give you the desired result, you make, this could be happening. And let's devise a strategy around that. So it's almost like making a guess. So is guess allowed in scientific process? Yes, definitely. Because to start the debugging, you need some seeding, you need some theory, some hypothesis to start with. So the hypothesis could be wrong, whereas you start with that and make some progress based on the other hypotheses, other speculations, and eventually come to a conclusion whether this is good or bad. So the difference between speculation and extrapolation is based on complete reasoning, and it is like, if this is how it is and this is the way it came, it should have been like this. So it's completely based on scientific evidence, deduction, whereas speculation can be a guesswork. It doesn't need to be 100% correct. It's basically resorted to have some path for the forward progress.
So finally, we have iteration. So we have formed a high-level opinion about what the issue is. We have isolated, we have backtracked, fabricated, and speculated. Now, when we started off, when the issue was first raised, we may have formed an idea in our mind. Okay, this must have been what went wrong. Now, iteration is actually the culmination of all of this. Using all of the postulates that we mentioned earlier, you are iteratively editing your problem statement to get to the actual issue. That is the exact definition of what must have actually happened. So every single procedure that you employ, every single methodology that you use is going to help you get one step closer to the final issue. What may have actually happened. So it can be entirely different from your suspicion in the beginning. So that is iteration. In iteration, you have the code, you have the different processes, you drive them together to finally converge at your actual issue site or what the actual issue was.
Yeah. So that's the postulates. Very high level, but I think this is the essence of debugging, and all abstract. We are not looking at how the concrete steps are yet, but this is where it will find its theory part of it. Any questions so far, please? Yeah.
Engineering process. So is this something that has been put down to a process in practice?
Oh, we don't know. We need to look at. We have seen bits and pieces of these kinds of things in various red books and other documentations. But what we are looking at, as I said, is 120 years of experience, which is spanning across hardware, OS, middleware, and things like that. So how do we codify all those things together? Yeah. I mean, honestly, I don't know if this covers the whole software spectrum or not.
These steps that you stated here,
Yeah.
5 or 6, they are basically a as an engineering process rather than just debugging as an art or magic.
Okay. All right. So now let's look at some of the concrete tools. We went very high level. Let's come to the ground now.
Okay, so first we have native debuggers. A very common issue that we all encounter is a crash. We all know what a crash is. An application is not performing the way it is supposed to. So after a crash, something called core dump or a crash dump is generated. On a high level, it is simply a screenshot of what went wrong. It will give you an idea about, it's like a screenshot of the heaps, the stack, the memory usage and everything. You can inspect that to actually find out what it was that went wrong. So post-mortem debug core dumping, that is after the issue occurs, you get a dump and you inspect it. Now, an important step here is to backtrack and to actually, we talked about isolation. So you actually backtrack, you will inspect the call stack and you can look at the core dump to determine what it was that went wrong.
Yeah. So next one is custom debuggers. Native debuggers are good for native applications like a C, C++ thing. So you launch it in GDB or DBX or WinDBG and start inspecting the call stack, registers, memory, blah, blah, blah. But when it comes to the modern languages such as a managed runtime, Java, Python, JavaScript, etc., they are not native applications. If you launch those in GDB, you don't see anything. Anybody has any explanation for that? Why you can't use GDB for Java debugging, Java crash dump debugging, Python crash dump debugging? Because the reason being, they are not native applications, they are interpreted in between. So what you see when you load it in GDB is the stack or the interpreter, not the actual application. The actual application is processed in between, either through the compiler or the interpreter. Whereas in C case or C++ case, the pristineness is still preserved and the GDB understands what are the call stack, what are the registers, etc. So custom debuggers are extensions to the native debuggers, which understands the native stack as well as the virtual machine in which this application has been executed. So in our case, JVM. So a debugger which understands both the native stack or native context as well as the JVM context.
Okay, so next we have replay compilers. So if you guys know, this is a black box. So after a crash, a black box is generally used in flights to know what it was that went wrong. So similarly, replay compilers perform a similar function, that is to record and replay the portion of execution. So many times the backtracking and the live debugging that we do, it may not provide us with a solution. Like I said, for enterprise level applications, there is too many lines of codes, and if your problem site is say like 20, 50 caller functions away, it is manually impossible to reach there. So in such a case, you may need a replay of what went wrong. So for that, we use the JIT replay compilers. So they kind of like record the entire process, the entire execution, and will give you sort of like, it's as if you were there when it happened. So it will give you a complete picture of what it was that went wrong right from the trigger point. So this is mostly useful when the behavior is isolated. That is, there was a particular trigger point from where the issue originated. In such a case, these compilers become very useful.
Yeah. And another one is decompilers. I think people will be familiar with this. Decompilers do the exact opposite of the compilers, which is compilers does translation from source to binary. Decompiler converts back to the source. The most common one is JAD, Java decompiler. So what is their purpose? Purpose is like this backtracking fails, extrapolation fails or becomes absolutely hard. Millions of lines of code. Where do you backtrack? I mean, it's possible, but you have other jobs to do, right? It's not just one customer case you need to deal with. So, and another scenario is the problem itself is conversion between the source and the binary. Like at the Java C level, the compiler level, the virtual machine level, so low level, we are always trusting the compiler, thinking that it's always going to do the right thing. But compiler is another software. Virtual machine is another software. They all can have bugs. So if the bugs are somewhere entangled between these two components, how do you debug that? So this is one of the things that will help you provide the source code, and then you can compare with the bytecode and see if the translations happen correctly or not.
So next we have profilers. Profilers, as the name suggests, so what is a person's profile? What you have done with your life? It's basically something that tells you who you are as a person. Similarly, profilers are used for application performance monitoring. It will give you an entire information about how it is that an application performs in terms of memory, I/O, and heap stack, everything. It will the shared libraries. So a complete monitoring of the application's performance. This is useful in many cases where you want to find out if the misbehavior is due to certain performance metric that is going wrong, or certain performance metric that is not meeting the baseline that is generally set to meet good performance. So profilers generally, it's basically used for performance monitoring.
Yeah. So that's about the tools. We choose some of the tools looking at the most common problem symptoms and looked at what are the most common tools that would address those anomalies. It's not the full list of tools, it's a representation for each. For example, the profilers are for the performance, native debugger are for the crash, things like that. So that's about it. I think it's little easy. Now, any questions on this theme? Yeah. We have JIT replay compiler from OpenJ9. So what that does is you have a flag to switch on saying that I want to replay when these thing happen. So for example, a method is supposed to be faulty, but you don't have a proof to that. Whenever this method is coming into execution, that's where we see the anomaly. So if you want to start suspecting that, switch on the replay compiler when this method gets into action. So once that method exited, you have the black box or the dump. Then once you load it in the JVM, instead of backtracking, it will forward progress just like any other execution, and which you can examine at different control flow points. So forward progress is always better than backtracking. Thanks for asking that. Yeah.
You say debugging code.
Yeah.
Are you talking about the dump files?
Yes. So codumps are also known as system dumps, crash dumps. Yeah, it's the same thing. Eclipse cannot be used. Yeah. Eclipse is for live debugging. Yeah, this is post-mortem debugging. Once the application crashed, you need to examine the various aspects to look at that. GDB, DBX. Yes. Yeah. Thank you.
So we have a crash, which is one of the most commonly encountered misbehaviors. So what you can do in crash is basically a combination of all that we have discussed. Backtracking to catch the origin. You do your proper live debugging. You suspect that a particular area of the code base is associated, that is where the issue originates from, and you walk back. You inspect the functions, their caller functions, and eventually you iterate it till you reach the source of badness or the point from where it originated.
Yeah. Freeze. Next one is freeze. Most common, hang. People call it hang, freeze, or low CPU. Low CPU meaning when you examine the application profile, the CPU usage, you see 0. Whereas the application is expecting to run. So that is where the freeze happens. When there are a lot of transactions, but transactions are not moving. We believe it should be processed, but nothing is happening. So what is a common diagnostic approach? List all the threads. Threads may be in waiting stage. If threads are running, you can't call it a freeze. Why? Threads are running, threads run on the CPUs, and CPU will be exercised. You cannot have low CPU at all. So what is low CPU? Anything below 5%, 2% is termed as a low CPU in a typical web application. So look at all the waiting threads. See why are they waiting. Mostly you will see a object upon which they are waiting, and the object which is being wait upon will have an owner thread. Now look at the owner thread and see what the owner thread is doing. Owner thread may be doing something which is very, very slow, and because of which a lot of waiters are sitting over there. Or owner thread may be in turn waiting for another object. which in turn may be owned by another thread. So repeat the whole process until you see the culprit thread or the slowest thread upon which the whole other threads are being piled up in waiting. It's a common hang diagnostic practice.
So next is a loop or a high CPU, the reverse condition. So optimum CPU usage is anywhere between 20 to 80%. So anything beyond or below that is bad. In this case, a high CPU is when it exceeds around 80-85% of the CPU consumption. So let us take an example of a scientific computing. You're performing a complex scientific operation. Obviously, the CPU consumption or the usage will be very high. It is to be expected. But now think of a web workload where it is mostly communication that's happening, IO bound operations. The CPU bound operation is comparatively low. So what do you expect there? The CPU consumption is going to be low. But in contrary, if you find a high CPU condition, say there are mostly only IO bound operations, but something is happening. That means obviously it is stuck in a loop. It is not able to come out of it. So in such a case, you can always almost assume that there is some loop, there is some iteration that is continuously happening, and the process is not able to come out of it. So in such a case, again, you backtrack and you will list all the threads, and you should inspect till you reach the point where in many cases it must be a very small variable change or an infinite loop condition, which will be a very minor change actually. So just correct it, and in most cases a high CPU can be solved using this method.
Yeah. Next one is poor performance. So unlike the previous anomaly scenarios, performance is a different beast altogether. Why? Because when you say poor performance, what is the criteria? How did you term it as poor? What is the best performance or what is a good performance? So you need a baseline, right? You need a baseline from which you can compare and assert that this is performing poor. So the baseline is nothing but a set of numbers tagged against various profiles such as thread profiles, method profiles, memory profiles, CPU profiles, network profiles, and things like that. In a good scenario, how network usage has been for your application, maybe 200 KB per second is the network health, the network traffic in a good health condition. Similarly, 1 GB of memory usage is termed as good. This is absolutely personalized for your workload. It cannot be generalized. It is on per application basis. And when your application version changes, this baseline has to be changed. Simple common logic. So once you have established the baseline and then you start seeing poor performance, what you need to do is start profiling each of these and make comparisons against the baselines and see which one is performing poor. Is it the memory which is exceeding the baseline? Previously it used to be 1 GB or 1 MB usage at peak load conditions. Now you see 4 GB. So clearly memory is a culprit, and apply one of the techniques that we already talked about to actually pinpoint the issue.
So next is memory leak. The capacity or the it happens when the system's memory capacity is exceeding. Again, this is something that is relative. So the first step here is to baseline steady state memory. What can you call a steady state memory? You need to know that. For that, you need to know what a good case of memory capacity is. So beyond that is what you can call a memory leak. So in this case, you can the method you can follow is to collect a heap snapshot and locate the growing object. That is, you start from a place where you suspect the problem is happening, and you go to the next caller function and so on and so forth till you reach the original dominator tree, or from where this object is actually being referenced. So this is actually an iterative process. You will have to repeat it continuously till for all the growing objects in this manner till you reach the area from where this memory leak is occurring.
Yeah. Did you like the picture, by the way? So they say that in good presentations, you don't put a lot of text in the slide because people's attention will be split between reading the text and listening to the speaker. So put some pictures so that you get the idea very fast. When we did the rehearsal for this slide, what happened is I didn't listen to her. I didn't read the thing. I was only looking at the picture. So it's so, I mean, I liked it, so impactful. It's like, hey, come on, when this is going to break out and the whole water is coming out, sort of a thing. So, any questions? So, I think this is now cool because we talked about very abstract theories and then looked at some of the tools, and then we combined them together to see how these tools can be used in appropriate manner for each of the anomaly situations and how they can be resolved or identified to an extent. Yeah.
Your experience, you have seen an application that has a high CPU and a high IO. What has been the, like you told,
Yeah.
85% figure that you gave, graduation, but you have a high IO and a high CPU
Yeah.
based application, your experience, what has been your point where you said this is the exact point which your market need? Because 90 for a high CPU, high IO is not.
Okay.
What figure do you tell me? I just want to know that, okay, what you said 80 is good, 70 is good.
Yeah.
So from your experience, what's the like number that you're looking?
Okay. So the a decent answer is it depends. It depends on the workload characteristics. As she said, if it is a scientific computation, you are utilizing the whole CPU that is allocated to you by the operating system. So the thread is continuously executing instructions, be it natural language processing or arithmetic or whatever. It gets some 10 millisecond or 20 millisecond from the OS allocation, and it's not yielding the CPU at all. When it comes to IO, IO is very, very slow compared to CPU bound operation. It's like 1 millisecond versus 150 millisecond comparison of CPU versus IO. So in most practical scenario, what happens is when IO occurs, the CPU is yielded. CPU is given to somebody else. So in a highly IO-centric application, you will see on an average 20, 30, 40% as a good health condition. If it is a scientific application, 100% CPU, no problem. It's a good indication because I'm utilizing the whole CPU given to me. There is no IO, there is no yielding. These are two extremes, but depends on your application. You can actually see what is a good health. Thank you.
I think another thing is the GC configuration.
Yeah. Yeah. Yeah.
Even though we may not have a memory leak, but if the generations are not configured,
Right. Everything is good, application is good, healthy, it's creating objects, deleting objects, but a misconfiguration in GC would make you feel like there is so many things happening in the application because back-to-back GCs are happening. GCs are not free. A lot of threads are running. A lot of CPUs are being exercised just to churn your memory, just to churn your objects for no reason. So configure the GC properly and make your application healthy. Thanks for pointing that out. Yeah.
Okay, so first we have simulative programming. This is actually one of the most followed or one of the best local recreation methodologies because here, so like I mentioned earlier, in production, if there is an issue and sometimes backtracking is not possible when it's a huge code base, you can go for simulative programming. The thing is, you cannot ask for diagnostic data as such from production because it can take a lot of time. And in many cases, the production will wait for the issue to occur again. So we don't have that sort of time. So mostly in simulative programming, what you do is you isolate, you bring down the size of the code to where you suspect the issue is coming from, and you debug from there. So abstraction and isolation, both the postulates are being used here. For example, in order to know that it is simulative programming that you need to use, you need abstraction. You need to be able to define the problem, and then you go down, bring down the size, narrow it down, and you will try to recreate it in your local development environment in a mini scale. So mostly the use cases are exceptions, errors, and crashes.
Yeah, thanks. So that reminds me that we missed to provide an introduction to what theme this is. So as I said, local recreate we are introducing as a very powerful form of debugging. Why local recreate is important? Because if you're trying to diagnose a problem with the help of the customer is running in production, and that means it's not easy to put your instruments or forget about anything, just collect the log itself. You need to wait for days or weeks. And if you want to apply some instruments, you need to wait for weeks or months based on how critical the business application is. They need to look for a maintenance window. They need to look for a replication, and so many things are there. for debugging a tiny piece of problem. What if you replicate that in the local lab, right? Two things will happen. One is the diagnosis will become super fast. Secondly, because you are able to have the problem locally, you will be able to verify the fix, and that will make the most comprehensive fix that you can think about. So for that reason, we strongly recommend try to do a local recreate for any sort of problem. So the theory says that every problem can be locally recreated. So next one is call stack assimilation. Call stack assimilation is a simple technique. We just coined a name for that. Look at the production call stack and see, go down the list and see which is the public API and write a test case that will exercise the public API. Expectation is that the public API will go the same path as that happened in the production. In many cases, it happens. Yeah.
So next is reflexive or brute force invocation. This is sort of a continuation of the callback assimilation. Imagine, I'll give you a very simple example. In production, there was a function A calling B, calling C, and up until D. So some issue propped up at D. Now we need to recreate it locally. So in our environment, for some reason, what if we are not able to reach D? So, but reaching D is very important because we need to recreate the issue which occurred at point D in production. So what we use in development is obviously some faulty method is not allowing the call from maybe A to B or B to C. So what we do is we use our brute force. We write a small piece of code, which again brings us to one of the postulates that we talked about, fabrication, wherein we tweak the code to recreate the issue. So here we will write a small piece of code to actually call the method. We are interfering in between, calling the method to see if we can recreate it. So now you may ask, we are entirely changing the code. This is not what happened in production. But that is not the way here. What we need is a solution for our problem. So if we are able to recreate it without changing the logic of the code, that is most important.
Yeah. Relay injection, this is a common practice. So think about multiple threads accessing a shared data, and you encounter hangs or multi-thread re-entrance related problems. The shared data is not consistent, things like that. So it's a race condition. How do you recreate this problem? You write a small code and you try to execute that. You always see that thread 1 is executing always first and then thread 2. Whereas in production, it is coming in either way, because of which the problem is manifested. Whereas in your local environment, it's never coming because thread 1 is always getting the priority. What could be the reason? There could be several reasons, like the systems in production and development are totally different. The CPU configuration is different. The scheduling priority, OS configuration could be different. The load in the system can be different. So there are so many environmental factors through which you will not be able to simulate the production exactly. So in which case, what you do is add artificial delay in one of the threads, right? The whole idea is to bring in two threads together or in reverse order. So the principle here is you can never depend on a shared data to be executed by multiple threads in a specific order. In whatever order they come, it should be, keeping its integrity. That's the theory, basic theory. So we are exploiting that theory to add a delay.
So next is binary fabrication. So this is mostly used for virtual machine and compiler anomalies. So whenever there is a version change, backward compatibility is usually an assured feature. You naturally assume that your old code should still be able to run. Imagine that a customer has migrated to a new version and for some reason he is unable to run his old code. So this is not supposed to happen. It's an anomaly. So what we can do is we actually, in this case, we go into the binary and we change it manually in order to recreate the issue and to see what it is that went wrong. So a very simple example is to, if your old version is not running, you just take the new version, you go in and you make a small version change. So binary fabrication is sort of like a change or a tweak produced in the binary to recreate the issue.
Yeah. So with that, we covered the 4 high-level themes. Like we looked at the theory, the postulates, looked at some of the tools that are commonly used, looked at the methodologies with which this tool can be employed to actually attack the issues. Then we introduced the local recreate as a powerful way of debugging. Now with that, we will look at some of the interesting real-world field stories and see how these methodologies are mapped into that and how we could actually get into the root cause of the problem in a very realistic as well as manner in which this can be exemplified for other similar scenarios.
So first we have unbounded RSS. For those of you who do not know what RSS is, let me give you a small background. RSS is residence set size. So we all are aware of, it's related to memory. So we all are aware of virtual memory allocation, right? Now, RSS is different from virtual memory allocation because virtual memory allocation is just an idea of the total memory that is being allocated. Whereas RSS or residence set size is significant in that it is actually telling us about the active memory allocation, which processes are currently using the memory. So how this is significant to us is in cloud-based systems, most often the consumer will be charged based on the memory that they are consuming. So RSS is an important criteria or a performance metric using which they are able to find out how much memory that the consumer is used, and based on that the consumer will be charged. So the consumer basically came to us with an issue that the RSS is spiking but it is not falling down. So this was a critical issue and the consumer was obviously worried because a high RSS all the time means they are going to be charged even during the non-transactional hours. By non-transactional, let me talk about a banking application. We all know that maybe 9 to 5 is the peak transaction hours. So naturally, we should assume that this is when the memory should be at highest. So during the non-transactional hours, naturally the RSS should come down. Otherwise, the consumer will be unnecessarily charged. But this is not happening. Now, this was a severe issue. Now, RSS is actually based on Java heap. So you cannot use the native custom debugging tools. It is not possible. So the only way to recreate this issue, so whenever we have a problem, the first thing we need to do is we need to be able to recreate it to find what went wrong. So in this process, so in this case, we were not able to use any of our default debugging tools as such. The only way was to go for simulation. So now we tried simulating it in two different boxes, and let me call them box 1 and box 2. So in both of these boxes, two different behaviors were observed. So in box 1, the RSS went high for the high transactional hours, but it went down during the non-transactional hours. So that is an expected behavior. Our aim here is to recreate the issue, right? We do not want the RSS to come down. In the second case, the RSS went up, it stayed there, but after some time it went down. So both of these were inconsistent with the issue that was that occurred during production. So, but then we were not able to recreate the issue, but the two different boxes showed inconsistent behavior, which made us compare them both. So this comparison led to the eventual conclusion that RSS cannot be used as a metric to evaluate the memory consumption. That is, it cannot be used in a cloud-based system, and you cannot charge a consumer based on the RSS, because a change in RSS will only occur when there is an actual demand. When there is a high demand, that is, say a process is using high memory and there is an inactive process, so the memory allocated to the inactive process will be allocated to the process that actually needs it, the one that is active right now. This is called paging and swapping. So here RSS does not change if there is no demand. So there may be changes, but if there is no demand, RSS will stay as such. There will not be any change in it. So that means it cannot be used as a performance metric for charging the consumers. So in this case, we were actually able to provide an issue or an explanation as to what is happening. But the question still remains as to what then is a good metric that can be used. So the answer to that is still unsolved, but yeah, we were able to give a good explanation to the consumers.
Yeah. So it's as good as, we didn't find any documentation which talks about RSS is not a good consideration, good metric for the cloud, for the memory usage, but that is how it is. So the bottom line is, don't rely on RSS. We haven't documented it publicly, but this is the fact. It's very funny. It's true. We trust RSS thinking that that's the true reflection of memory usage. It is not. If your cloud vendor is metering you based on active memory, you know the hint, you know what the question to ask. So Great revelation. Any questions on this? If yeah. The so the test case was sufficient to convince them. We wrote a native program, C program, and gave it to them. So they ran it, they understood it was perfectly matching with the explanation. The problem is not convincing them, the problem is how to solve this. Because in the entire world, cloud meters on RSS. So it's not easy to change. It's customer's problem, not our problem. Yes. So virtual memory, you know virtual memory, right? When you allocate memory using new or malloc, whatever, you get virtual memory. So you think this is all your memory, but only if you're actively engaged on the memory, it becomes your memory. If you're sleeping, say for example in the night time, for a banking application example that she took, you are not doing any active work. Whereas if other process run in the system needs memory, they will steal this from you. They will put a copy in the disk and take this memory, this page, and use it for their purpose. Whenever you want the page back, it will be swapped in. So this concept is called paging and swapping. Yeah. So RSS by definition is the memory which is still in your account, memory which is not paged out, which we trust as the true reflection of your usage. But with this exercise, we found even that is not a true reflection. Because if there is no load in the system, no paging happens, the RSS that grew up to this level stays there. Yeah. Okay. Question to you. How do you relate this image to the theme? Yeah. Okay, close, yeah. So my interpretation is seemingly very much growing weeds. I mean, some concerns, amber in color, so something concerning, but at the end of it, it's found to be all green. Trees are green, so nothing to worry.
So the next one is stream corruption in Hadoop, Spark, or Kafka. So we know, so here this issue was noted in PPC or Power PCs. So Power PCs are very powerful, sort of similar to supercomputers, which can perform massive computing, parallel computing. So obviously a customer would purchase it to bring down their cost or to perform massive parallel computings. Now, we know that the Apache framework, it is for the stream processing and distributed computing. Now, so the story goes like this. The customers, they purchased PPCs from us and they performed a word count sanity testing audit. So word count is a small sanity test similar to a Hello World program. It's as simple as that actually. But it was observed that the word count program was failing. It is actually a sanity testing for Apache based applications. So now the word count problem was failing. Now this was a huge concern for something like a PPC, and the customers asked that we take it back because it was, so if such a small problem is failing, it is of no use to them. So now this is actually, this was a problem which had very high impact. So a CritSit was formed. A CritSit is basically a critical situation team which is formed in such dire cases where developers from different teams and experts are brought together temporarily to solve a very problem which is of very high business value. So the CritSit, they examined the hardware, they examined the middleware, and they eventually came to the conclusion that the problem was in the call stack. So when they examined the call stack, they found that the problem was in the way the object serialization was being performed. So then that was inspected further. We went in, and the issue was that the header serialization was bad. By bad, I mean to say that the header was getting reversed. Now, if this were a random issue like a normal crash or any other problem, say we were able to recreate. So one highlight about this issue is we were easily able to recreate it in the PPC. That was one thing. Another thing was that in the 2 instances, or maybe 3 or more instances in which we tried to recreate the issue, in all of the instances, the output or the issue that we received was same. that is the header was getting reversed. Now, if this were a random issue, each time the output would have been different. So the fact that the corruption is consistent led us to believe that there is some issue is happening due to which the header is getting reversed. So further research was done on that, and eventually we came to the root cause, which was very simple. That is, I talked about PowerPC. They are different from Intel architecture that we use. So the thing is, the people who developed the word count problem, they never tested it on PPCs. They only tested it on Intel, where little endian byte ordering system is used. Whereas in PPCs, we use the big endian system, which is just the reverse. So if they never do it on PPC, an issue is never going to come, and they did not know. So finally, the solution was just a line of code, that is, if it is a PPC, to just reverse the byte ordering. So it was a very big issue. It had high business value. It was, but finally, the solution was very simple. So this is what we want to iterate here. That is, the issue may be large, but by following these methods, you can eventually reach a point where so this was just a line of code that had to be changed. But to reach there, the method and the structured way in which you approach the problem is very important.
Yep. Thanks for explanation. One of the IBM learning is the business complexity is not necessarily proportional to the technical complexity. So don't get panicked if there is a $1 billion customer pounding on you saying that, hey, our things are impacted and come and solve it. So definitely you might be involved in a big team, but the whole idea is not to lose the track. If you are the forefront developer who is attacking the problem, just stay focused, look at the problem without keeping the business impact or the customer profile into the consideration. If you do that, you get panic and you do several goof up. Like by evening, I need to make an update. So let me give an update for the sake of it. You may not be attacking the problem. If you stay cool, you get it together. This is one of the classical example of that. 70 million was at stake. They asked us to take back the machines, and the whole software division was panicking, and no team was able to perform properly because of the pressure. But eventually we cracked it just by looking at the problem. Was very simple, never tested in that particular platform. So very interesting case study. We applied the abstraction, isolation techniques which we talked about in the beginning. You stole my previous slide, so you take it. Go ahead.
So JUC hang or Java util concurrent hang. So this was again, this was reported in PPC. There were large multi-threaded web app freezes. So the issue was that the app is completely unresponsive. There is 0% CPU consumption. So this was not supposed to happen. And next slide. Yeah. So here, obviously, the problem determination method was to see how the thread stacks were packed. We earlier talked about low CPU, the method that we use. We will observe the threads that are being blocked or those that are not running, and we will inspect them to see which object that the thread is waiting upon. Now, if you reach that object, almost always that object will have an owner thread. So now you go to the owner thread. So this is actually an iterative process. You will continue this, you will repeat this till you actually reach the faulty object or you reach the root cause from where the issue originated. So in this case, when we finally reached the object, we saw that it was free. That is, it did not have an owner thread. Now, an object has a lock word associated with it, using which the threads that are waiting upon it are able to access it. So when there is no lock, the threads are not being able to access, and then we contacted the JUC author, Doug Lee.
Doug Lee, yeah.
Yes. So we contacted him, and apparently he said that such a state is impossible. This is simply an impossible scenario. Now, please make note of this private volatile in state that actually shows the log state of the object. So it keeps swapping values. When the state is 0, it means it's unlocked, and if it's 1, that means it's locked. So next slide. So finally, the issue was that PPC follows a weakly consistent memory model. So you have your cache and you have your main memory. So whatever happens inside a cache is specific to that particular CPU. So here, in order to get it to the other areas, it has to be flushed out to the main memory. So in this case, for some strange reason, it was determined that this particular object's state was not being flushed out to the main memory, which means it is not, so there is no way the main memory can know. So usually the flushing happens by default, but here there was need for an explicit flush. Now, finally, how the problem was resolved was that instructions were inserted to flush out the state in order to lock it, and the methods that were used in this case were local recreation, of course, abstraction, isolation, and iteration. So even in this case, just a few instructions to flush out the cache onto the main memory helped us to resolve the issue.
Yeah. So from our perspective, the summarization of this session is very simple. Engineering, we know, is creativity. Development is creativity, and then debugging is super creativity, because it needs more power than what you used in the development. You need to backtrack. You need to actually recreate, reproduce the development environment and the design that the developer used in a virtual world to actually see what is going on. You need to understand the design and the indent from looking at the row dumps and other artifacts like profiling the threads and profiling the methods. You're looking at the system, observing the application from various corners and figuring out what is the indent, what the application was doing. So that requires a lot of skills. And the thing that we actually described, the methodologies and the postulates, are the ones which are going to help. One of the key debate in the developers world is what programming languages and frameworks that I should be mastering to stay relevant ever. The simple answer is no language and framework. It keeps changing. It's trendy, and today is X, tomorrow is Y. So that is not going to help. What is remaining in you is the engineering skills, the core skills of debugging, developing. And that means a lot of logical reasoning, ability to define the problem, ability to define the intent, ability to compare, contrast, evaluate, and make theories, prove the theories, disprove the theories, and come up with compositions and creations. So that's the one which is going to stay forever. Once you are mastered in the art of that, any language, any framework, any tool will come handy for you in weeks' time. So that's the message for the developers, and that's coming from the years of experience that my company, our company, has acquired, and that's one of the reasons why we say client value is the highest organizational value. So that's the one I want to conclude with. Thank you very much.